Moving on with chapter 2, we talked last time about inductive reasoning, which is forming a conclusion based on patterns, right? Whether it's in data or any kind of pattern, so pattern recognition. We're going to make conjectures and not always know if those conjectures are true or false. Talked about counterexamples and all that stuff. We're going to move ahead and talk about deductive reasoning today, and the difference between inductive and deductive reasoning. And then we're going to talk about some of the postulates that sort of form the foundation of some of the theorems that we're going to see later as well. And biggest thing there is being able to draw them to represent what those postulates are saying. Okay, so let's start with deductive reasoning. Okay, and the definition of deductive reasoning is the process of showing that certain statements follow logically from agreed upon assumptions and proven facts. And so that's the thing, right? We're going to use agreed upon assumptions and proven facts. And that's the difference between inductive reasoning. Inductive reasoning, we're just looking for a pattern. Here, we're going to take things that we know to be true and form a conclusion. Okay? The difference can be seen here. So we've got this data over here. And this is information on the northern elephant seal. The depth, so a seal was observed, and some depths were marked, and then how many strokes it took for that northern elephant seal to get to the surface. And this is information I'm sure is useful for whatever reason. Okay? And the difference in inductive and deductive reasoning is basically the difference in what's going on in this graph. Okay? We have actual observed points here, here, here. These are the facts, right? And the conclusions we make are either going to use those points, which are the facts, or they're going to use this pattern or this trend line that sort of fits this pattern, right? We did trend lines in Algebra 1, but that trend line. So are your conclusions based on this trend line, or is it based on the actual data points, the facts from those points? Okay? And so the first conclusion here says that the northern elephant seal requires more strokes to surface the deeper it dives. Well, and if you see this in the graph, that's the trend of our data, right? It's not true for every data point, but it's the trend, right? And we don't know what happens after 500 meters with that elephant seal. So since we're using the pattern of the data, that trend line, to make this conclusion, this is your inductive reasoning. Okay? I'm using a pattern of behavior to come up with this conclusion. Now, if we conclude the northern elephant seal uses more strokes to surface from 250 meters than from 60 meters, now we can go to the actual facts at hand. Now we can go to the actual data and find the data point at 250 meters, which is this guy right here, and the 60 meters, which is this guy right here. And apparently, yes, it did use more strokes to get to the surface. And that's just from the facts that we have at hand. And so this conclusion was reached by using deductive reasoning. Okay, and that's the difference. Now, with deductive reasoning, there are some laws of logic. And there are more laws of logic than the two that we're going to talk about, but the two that we're going to dive into, one's called the law of detachment. And again, we're trying to make conclusions, and we're trying to make conclusions based on facts. The law of detachment says that if you have a true conditional statement, and then you know that the hypothesis happens, that means that the conclusion, we can conclude the conclusion, which makes sense, right? So in other words, if we know that Mary goes to the movies every Friday and Saturday, today is Friday, then what conclusion would we logically make? Well, the fact that Mary is going to the movies. That's the law of detachment. So from our conditional statement, we detach the hypothesis, and if it's true, then we can conclude the conclusion. Okay? That's the law of detachment. The law of syllogism is the other one. And the law of syllogism sort of has us recognizing a particular pattern in our statements. Remember that a hypothesis and a conclusion in an if-then statement are just statements. They're just pieces of information. So for the law of syllogism, we need two if-then statements, like A and B here. We need two if-then statements. And if they're true, that will lead us to a third if-then statement that we will also know is true. So if statement A and B are true, then we know that C is going to be true also. Now, there is a pattern to the law of syllogism that we have to be very leery of. And we use symbols to represent that pattern. So we're going to represent in this first if-then statement for A, the hypothesis we're going to let be P. The conclusion we're going to let be Q. So the first if-then statement says, if P happens, then Q happens. So P leads to Q. The second if-then statement uses Q also. So Q is the conclusion in the first if-then. Then we need Q to be the hypothesis of the second if-then. And then the conclusion we're going to let represent R, because it's going to be a different statement. And if Q leads to R, so if P goes to Q, Q goes to R, then our last if-then will link P to R. There's a lot of variables that we're throwing around here, and we'll see an example of this in a second. So basically what this means is, if the statement that is the conclusion of the first if-then is the hypothesis of the second if-then, then we can jump right to, we can skip that statement, and we can go right to saying that if P happens, R will happen, and that will be true. For example, here's an example of how we can use the law of syllogism. If Rick takes chemistry this year, then Jesse will be Rick's lab partner. So this is the hypothesis of the first if-then. I'm going to let it be P. Jesse being Rick's lab partner, I'm going to let be Q. So P leads to Q. The next statement, if Jesse is Rick's lab partner. There you go, we see it again. Rick's lab partner, Rick's lab partner. So this is our Q. Then there's a brand new statement, Rick will get an A, and that's our R. So that means P or Q leads to R. So P goes to Q, Q goes to R. That means we can conclude that P goes to R. And what that would sound like is, if Rick takes chemistry this year, then he will get an A. So we couldn't get there just on its own. If Rick takes chemistry this year, then he will get an A. Well, we don't know if that's true or not. But the law of syllogism used this Q statement also to link them. If Rick takes chemistry this year, then Jesse will be Rick's partner, lab partner. If Jesse is Rick's lab partner, then Rick will get an A, and that's why he gets to have that A. Okay, so it's linked. The conclusion of the first if-then has to be the hypothesis of the second if-then. Then we can link P and R and make that conclusion, and that will be true. Okay? This is not the law of syllogism. This is an example of not law of syllogism. If a polygon is regular, so there's our P statement, then all angles in the interior of the polygon are congruent. There's our Q statement, and that's a true statement. So P goes to Q. If a polygon is regular, so the same statement, it's using a piece of the first if-then, but it's the first piece. So this is P again. Then all of its sides are congruent. That's a new statement. We label that R. P goes to R. Well, the law of syllogism needs P to Q, Q to R. And that's not what this is. So we cannot use law of syllogism here. Okay? All right. That's deductive reasoning. Now we want to get into some of the postulates, some of the basics that we're going to sort of build our foundation around. Okay? A postulate. You remember what a postulate is? A postulate is a rule that is accepted without proof. It's just a commonly agreed upon fact. A theorem is something that we need to prove. It's almost like a conjecture. We've got to prove it. Okay, there's a difference between our two rules in geometry. Now, the basic postulates that we have. So these are things that we just know to be true. We agree that they're true. Are here. Okay, you stop the video for a second and to write them down if you want, and then we're going to talk about them and draw them out. Okay, so the first one, postulate 5, and I don't need you to memorize the numbers. The numbers are irrelevant. If you open up a different geometry book, then those numbers in there would be different. Okay, so the numbers are not important. We may use them to reference in our notes, but we don't need to memorize them. Just know what the postulates say. And postulate 5 says, through any 2 points there exists exactly one line. Through any 2 points. So I would need 2 points. A, B. There exists exactly one line. So I would need to draw the line that goes through those 2 guys. And that's the only one there is. Okay? Postulate 6 kind of goes the other way, and it sounds like it's saying the same thing, but it's not because of that phrase "at least." So postulate 6 says a line contains at least 2 points. A line. So we've got to have a line. And then what we know about that line is it contains at least 2 points, and at least suggests a lot more. So just because we need 2 points to name a line doesn't mean those are the only 2 points on this line. As a matter of fact, there are an infinite number of points on this line. You can just keep labeling them. Okay? That's postulate 6. Postulate 7, if 2 lines intersect, then their intersection is exactly 1 point. If 2 lines intersect, there's 2 lines, L, M, then they intersect at exactly 1 point. We can call that A. Okay? And you guys actually were using this postulate to find points around the room when we first did that back in chapter 1. Okay? All right, some more postulates. Again, stop the video for a second, get them written down in your notes, and we're going to talk about them, draw them out, and then start using these postulates. Okay, so postulate 8, through any 3 non-collinear points, there exists exactly one plane. Through any 3 non-collinear points. I need 3 non-collinear points. There exists exactly one plane. So if I've got 3 non-collinear points, and we've made a big deal about that so far, got to be non-collinear so that we can have exactly one plane. If they're collinear, there are an infinite number of planes that those guys will sit in. Now postulate 9 is kind of like the 2-line postulates from before, 5 and 6, that they sound the same, but they're kind of saying some things differently. So a plane contains at least 3 non-collinear points. There's that phrase "at least" again. So a plane, we've got to have a plane. Then we know that it contains at least 3 non-collinear points. We know it contains a lot more. It contains an infinite number of points. It makes a lot of sense. Okay, that's how we would draw it out. Postulate 10, if 2 points lie in a plane, so if I've got some plane here, and I've got 2 points in that plane, point A and point B, then first we know that there exists exactly one line through those 2 points. But what this postulate says is that that line also is in the plane. So careful how you draw that. Line L is going to still be in the plane. You don't want that plane to go outside the box, because then you start to make it look like the plane is not, or the line is not in that plane. So be careful there. Postulate 11 says if 2 planes intersect, then their intersection is a line. If 2 planes intersect, so we need to draw 2 planes intersecting. There's one. I'm going to draw the other. To look something like that. And remember, you're trying to make this a 3-dimensional picture, which can be tough. So I wouldn't see this. With this. And I think that's pretty good. But when 2 planes intersect, so plane K, plane R, then they intersect at exactly one line. So line L. Okay? And that's how we would represent that. All right, let's try to use these postulates. Identify a postulate illustrated by a diagram. So in this first diagram, if lines, then a point, which postulate is that illustrating? We've called this postulate, well, let's go back and look. Two lines intersect, so that's postulate 7 apparently. Okay? This is postulate 7, which says, and I'd rather you just know what it says. If two lines intersect, then they intersect at exactly one point. Okay? B, again, the postulate number I don't care about. We have to know that this basically is representing that if two planes intersect, then they intersect at exactly one line. Okay? That's what those diagrams are showing. And we're kind of getting into how to draw pictures, what can we assume, those kinds of things. Next one here. Postulate blank. Well, I don't know what number this is. I really don't care. Through any three non-collinear points. That's the most important part here. Through any three non-collinear points, there exists one plane. I think that was what? 8 or 9 or something like that. But again, I don't care about numbers. Okay? But that's the postulate that this is illustrating. Now we're going to start using a diagram to find examples of these postulates. First one, postulate 9, plane. Postulate 9, which says that a plane contains at least 3 non-collinear points. So look at that diagram. What plane contains at least 3 non-collinear points? Which one's showing that? I mean, we know that they both contain more than at least 3 non-collinear points, but which one's showing that? Can you see it? Hopefully you're looking at plane Q. Because in plane Q, you've got V, you've got Y, and you've got W. And those 3 points are non-collinear. Okay? Postulate 10. If 2 points lie in a plane, then the line contained in the lies in the plane. So what are the examples? Where can we find that in this diagram? Well, look at point Y and point X. They lie in plane P, and apparently so does line A. So there's your example of that postulate. Postulate 11 says that the intersection of plane P and plane Q, what is that intersection? It's supposed to be one line, and that line is line B. Okay? So those are our examples of our postulates. All right. Being able to sketch, and I'm going to change this. You notice you made a change in notes as well. We want to sketch this so that PW is congruent to WQ. And here's sort of the big main point here is being able to make good pictures, draw good pictures. And we've done a little bit of this already. Sketch a diagram showing line TV intersecting segment PQ at W so that PW is congruent to WQ. Go ahead and stop the video. See if you can't draw that, and then I'll show you what it should look like, and you can change it from there if you need to. Should look something like this. Okay. Oh, forgot my W. Segment PQ is right there with your endpoints. Is being intersected by line TV with arrows at point W, so that PW and WQ are congruent. Okay? Got to be able to draw good pictures and put in there what you can assume, right? We're showing it so that PW and WQ are congruent. If we just knew that TV was a segment bisector, then we would know those two are congruent. Okay? All right, talking about what we can and cannot assume. Here's another diagram. This is not in your notes. I think the picture's kind of tough to get to print out okay, but from this, right, take a look at these. Which of these statements cannot be assumed from the diagram? From that diagram, can we assume that A, B, and F are collinear? Yeah, we can, right? They're all on the same line. A, B, F on the same line. Can we assume that E, B, and D are collinear? E, B, and D. We can't assume that. They may look like they're collinear, but we cannot assume that. They may or may not. Okay, what about segment AB being perpendicular to plane S? Well, here's segment AB. Being perpendicular to plane S. Remember, perpendicular things form right angles. This right angle box right here allows us to make this assumption. So can we assume this? Yes. Can we assume that segment CD is perpendicular to plane T then? There's no right angle box, so that means no. And last but not least, line AF intersects line BC at point B. Can we assume that? Right? Line AB intersects line BC at point B. Can we assume that? Yeah, because that's their intersection right there. So yeah, we can assume this. Okay? This is what we can and cannot assume. And that's it for today. Homework's out in Canvas. Get that done by next time, and we'll see you guys then.